Thermodynamics part. I would like to start reviewing very briefly what we did in the last lecture yesterday. So you remember maybe that I had this table where on the one hand I had thermodynamics and on the other hand on the other side I had information theory. And then I told you that there are very different purposes of these theories, that they were developed for very different background. But also, I mean, thermodynamics, which is kind of a macroscopic theory, involves variables which are measurable directly, like pressure or temperature and so on. And then I said, based on these quantities, there is some other quantity defined, which is called an entropy, and I called it thermodynamic entropy. And I mentioned this definition that the entropy is defined differentially by an entropy change, namely by the amount of heat we add to a system. By the way, it has to be added reversibly, divided by the temperature of the system at the point where we add this heat. And in information theory, we have this. So the entropy is actually an element, or is a function of a density operator, or in classical information theory of a probability distribution. So here we refer to microscopic states, so to speak. So information theory is a theory that explicitly talks about variables that describe degrees of freedom of a system that we may not control, whereas in thermodynamics we never talk about these variables. So in some way it's remarkable that in thermodynamics, not in statistical mechanics, but in thermodynamics, the whole theory can be set up without knowing about, for example, the gas or the particle model of solid states or of gases. So you can develop thermodynamics without knowing what the continuum is, what matter is. And here we have this usual formula that I briefly write down. So, by the way, one difference, I mean, we will now establish a connection between these two. So I announced last time that we will try to make a precise connection between these measures. One thing that will happen is that because they were defined in different fields, there are also different conventions. So what we will find at the end is that there is a prefactor here, which is the Boltzmann constant. So the thermodynamic entropy has always a Boltzmann constant plus an ln2 times the information theoretic entropy. And this is just a consequence of the fact that in thermodynamics it's natural to think here of something that has actually a dimension, because here you're dividing energy by a temperature. Of course, you may here divide by the Boltzmann constant, then you would get a dimensionless measure. And this ln2 comes from the fact that in information theory it's very natural to take 2 as the basis of your logarithms. If I wrote here the ln, then of course I would get rid of this ln2 here. So this is also a convention that we use bits and not nuts in information theory as the units of information. Okay, so one thing we did now yesterday was to try to understand how we can potentially establish such a relation, despite the fact that one would sometimes think that entropy is maybe a more objective quantity than information theoretic entropy. So in information theory, we have very naturally a subjective view, because maybe you also know, or I introduced that briefly, there is this concept, for example, of a conditional entropy, which, by the way, for those who haven't seen it, is defined in that way. So it's the entropy of the total system and the entropy of the partial system. And this conditional entropy is usually interpreted, and by usually I mean you can also make that precise in operational scenarios, but the interpretation in all these operational scenarios is that it's the entropy or the uncertainty that B has about A. So you could think of B as knowledge you have, and A is the system which you're interested in. So you're talking about how much uncertainty do you have if you collect all information in B and try to make a statement about A. So that's the interpretation. Sorry? Oh, yes. Is there a question?
Very naive confusion, but since, as you said, they defined the entropy without knowing the microscopic
Mm-hmm.
why did it come out to be the natural log of the number of states?
Aha, this is not so relevant because there's also this KB, for example, here.
Because of Gibbs, it's e to the minus beta h and not 2 to the minus
Yes,
beta
you can, for example, see it like that, but that would already be a microscopic picture. But, I mean, you could say there's anyway a constant here, so it doesn't matter. But this would be the statistical mechanics explanation. Why? So in statistical mechanics, you would also have this convention here. Now, okay, this clearly, I mean, and there are many, I mean, it's probably clear in information theory. I made this example with a coin that I toss and don't show you the outcome, and then you have entropy 1 about the outcome, whereas I looked at it and have entropy 0. In that case, I would have two different entropies, depending on whether I condition on my knowledge or on your knowledge. So here we are always thinking these subjective terms. I also made some examples here, and because I had some other discussions with some of you yesterday, in the breaks, I think it's useful maybe to consider one additional example that illustrates the nature of this type of entropy measure. Also, maybe it's useful to familiarize yourself a bit with this type of entropy, which is really defined without referring to the microstates. And the example that I've chosen is a very famous example. It's the Gibbs paradox. And interestingly, I really like this example because I have some more personal connection to it. And I found I got an office when I joined ETH, and this was an old building, and I found some old notes of Pauli, who was a professor at ETH, and there was some cupboard that was always locked, and once I opened it, I found some notes, and he had some lecture notes on thermodynamics, and he actually writes a lot about this Gibbs paradox, and in some way resolves it. And for those who are interested in knowing what Pauli exactly said, there is a very nice paper by Janes, which, maybe I give this reference. It's called the Gibbs paradox. And there he, in particular, describes what, in a very nice and pedagogical terms, what Pauli said about the Gibbs paradox and how he somehow resolved it. I mean, you can always ask, what does a resolution of a paradox mean? It's just to better understand why it's actually not a paradox. But let me now explain what this paradox is, and it will somehow give you some additional insight on in what sense we should, on what it means when we say that this is maybe not as subjective as we may think it is in the first place. Okay, so what is the Gibbs paradox? So I assume that many of you, at least those who had physics or attended physics courses, have seen that before, but I guess there are also some of you who have maybe not, or don't have a physics background. So let me very briefly explain it. And I will try to explain it on a level which doesn't require much more physics than what we already used so far. So you can look at the following scenario. So consider a box, which I will later introduce some balls here, which has two types of particles in it. And I call them the plus particles and the times particles. So they're just two sorts of particles. So it's kind of a gas, a mixture of two types of particles. So, and it should be an ideal mixture. Ideal mixture means that on the microscopic level, that the particles don't interact. So as we saw yesterday, that also Scott likes a lot non-interacting particles and can do a lot with them. So here we also use non-interacting particles, which means, or I mean, in practice, you could, for example, think of two different isotopes of the same chemical material. Then they also don't even feel a very direct difference between them, but there could also be two different chemical components. Anyway, this doesn't matter so much, but think of it in such a way that the number of particles, so there's a fixed number of particle n, and the number of plus particles is equal to the number of times particles, so this should both be n half. And now we could think of some process, and I will now introduce a process because I want to apply this formula, and this formula only tells us something about entropy changes in processes. So this formula will never allow us to allow me to tell you what the entropy of a system is. I can just talk about differences between entropies. And now think of the following process. So assume that I have I find a material that allows me that has the property that the plus particles can pass through the material. It's kind of a membrane, whereas the times particles cannot pass through it. So maybe I use a different color for this material, maybe red. And I now create a piston from this material. So what I'm now going to do is to move that piston until the middle of the box. So I move it to here. And so the consequence of that will be that one, okay, I already forget which particles can pass and which not, but let's assume it's the plus ones that cannot pass. Or let's say the times. It's nicer if the plus remain on the left-hand side. So the times cannot pass, and the plus ones can. So there will still be plus particles on both sides, but all the times particles will be here because they couldn't pass. So I moved this thing in this direction slowly. And let's assume that I do this process while the system is in contact with a thermal bath at temperature T. Why do I need a thermal bath? Now, what I want to calculate is how much energy I need to move the piston from here to here. And of course, I need some energy, but the energy will not depend on the plus particles at all, because the plus particles can freely move through this membrane here. It will only depend on the times particle. So what I could do in order to calculate how much energy I need, I could just think of a gas which only consists of the times particles, because this membrane is completely transparent to the other particles. But this is a calculation we have done yesterday. We have calculated yesterday how much work it needs to compress a gas to half its size. This was the erasure process. Actually, the calculation was done in the opposite way. I talked about the Sealer engine, where you go from here to here, you let the gas expand. But what we found is that the work so here I have to put in some work, and the work that has to be put in, you remember, is this famous formula, Kb ln 2 times the temperature. But now we did it yesterday for one particle. Now if you do it for n particles, then I have to multiply that with n times. So this is this is the amount of work I need to go from here to here. Now I could, of course, also go a little bit further and do the same thing again with a different membrane that I put in from the right, so that at the end I end up with all plus particles being here and all times particles being here. So I just did now the same thing. So I assume that I have another wall that I insert here, and I move this wall slowly in this direction. And this wall has the property that all the times particles can pass through the wall, but the plus particles cannot pass through the membrane. And so then if I move it, I end up in this situation here. And of course, this calculation is the same. So again, I have to introduce some work, and the work will be n plus this time, times Kb ln 2 times T. So the total work that I put into the system is, of course, the sum of these two. And the sum is, here n plus n, or n times plus n plus gives n. So it's n times Kb ln 2 times T. So this is how much work it costs me to somehow separate, to unmix a gas consisting of two particles. That's also called the mixing entropy in thermodynamics. So the physicists among you have certainly seen that calculation before. So why is it interesting to us? Let's now look what that means for the entropy. So I said before that we assume that it's an ideal mixture. What does that mean on that level? On that level, it means that the energy of the gas, the internal energy, is the same here and here. So if I call the energy of the whole thing U, so this is the energy, then it's, and here maybe U prime, then the requirement is that U prime is equal to U. This is by definition what it means in thermodynamics to be an ideal mixture. So it's just a definition. If you don't, you just choose the two components in such a way that they have this property. And this is, for example, a property that an ideal gas has. Because for an ideal gas, the energy only depends on the temperature and not on, there's no interaction between the gas molecules. And if there's no interaction, the particles, of course, don't mind whether there are some times particles among them. The only thing that matters is the total density of particles. Now, if the energy is the same, the internal energy is the same here and here, then, but I put work into the system, this work has to have gone somewhere. I mean, energy is, of course, conserved. So what it means is that the work that I put into the system had to be dissipated as heat going to the reservoir. So in some way, when I did this process, it must have, in case that there was some outflowing heat Q, or maybe I draw it here. So there's some heat Q going into the reservoir, and in this process as well. So there's again some heat, and because the total energy has to be the same, the outgoing heat has to be exactly the same as the work. So the heat is the same as the work. Oh, maybe actually this was a little bit unfortunate, because one convention in thermodynamics is usually that I always draw the arrow, I mean, although the heat is going out, I draw the arrow of heat into the system, and then say that this is negative. So, I mean, we just call, I mean, the convention that I'm using here is that energy, whether it's heat or work, going into a system is positive. And because now the heat is going out of the system, it's the negative work. But you see, if I add the heat and the work together, it gives 0. So the total change of energy is 0. Okay, maybe now I can use this formula. So this formula tells me that I can now calculate the entropy, because I know how much heat I lost. So this is a differential formula, but I can use it to the total process. So what it tells me is that the entropy at the end, so let's call the entropy here, so this would be the initial entropy, the thermodynamic entropy, and S prime is the entropy at the end of the day of this process. So the entropy change is, of course, S prime minus S, is now by definition, so here I can just integrate over that, because the temperature is by assumption constant. So this differential definition, so this is defined for infinitesimal heat flows into the system. But if I integrate that up, I can do that very easily because the temperature is constant. So it just tells me that the total entropy change is given by the total heat flowing into the system divided by the temperature. So this is now given by 1 over T times this thing here. So that times minus that. So I put the minus here. The total thing was here. The N, KB, ln2 times T. So the T cancels. So in other words, the entropy change is exactly this thing. N times KB ln2. Okay, so that's, in other words, or let me now summarize what we have calculated and write it down cleanly. So this was just a calculation that was probably boring for those who have already seen it, but now we will come to the interesting part, to the paradox. So what have we now calculated? We have calculated the following thing. We have now two situations. One situation, let me maybe start now from the right. One situation is this one. And of course, once I have this picture, I can, of course, insert here a wall and separate the two compartments. So I could think of it like that. There are two boxes. One box contains the plus particles, and the other one contains the times particles. And these boxes have some entropy. And because the entropy reference point is not fixed, I can always start from something. Let's assume that this box has some entropy SA, and this box has some entropy SB. And so what we calculate, and the entropy, so the entropy of these boxes together, how large is it? How does it relate to the entropies here? Does anyone see that? So what should I write here on this side? Here it should be just S prime, because the entropy of that system is, of course, the same as that one. There's no difference. I mean, I can go from here to here in a reversible way, because the particles are separated. It's just taking the two compartments apart. So this is S prime. now we have another system, which is the one we started off with. So this was the system where we have a mixture of particles. And here, this is the entropy of this system is what we called S. And what we calculated just here is that S, if I'm now writing down this formula here, then it tells me that S is equal to S prime, but S prime is SA plus SB plus K plus N times KB ln2. So I now used just this formula here to write S, the entropy of this system, in terms of the original entropy. So what does the formula tell me? The formula tells me that if I have two gases, with two different components of a chemical substance, and I put them together in a larger cylinder, I mix them, so I put them together and open the wall here, then the entropy of the final state here is the entropy of the individual systems plus an additional term. And this is, as I said, the mixing entropy. So that's what thermodynamics tells us about the entropy of such systems. So this is now an application, so to speak, of this definition. So what I used here is I only used this definition together with the experimentally verifiable gas law, which told me how much work I need to do that. So this is a direct consequence of the definition. Okay. So far we don't have a paradox. It's kind of, it even makes sense from an information theoretic viewpoint, because if you get rid of this, so I told you this factor is just a convention. So you see that the entropy of the mixture is somehow the entropy of the individual parts plus n, which makes perfect sense, because in this mixture you lose exactly 1 bit of information per particle. Because here you knew for each type of particle whether it was left or right. You knew that all the pluses were left and all the times were right. And you lost this information here. So for each individual particle you lost exactly 1 bit of information. And this is exactly what this formula tells you. So here everything seems to be in agreement with our intuition, even in statistical mechanics. But note that this derivation was only in thermodynamics. And by that I mean we never used anything about microscopic states in this whole derivation. I mean, I used the gas law, but the gas law doesn't require this number n here. I could just formulate it in terms of mole and so on. So I didn't use the fact that there are really microscopic states. Now, let's now look at a different situation. And this is where the paradox arises. So let's now assume that we have a much simpler situation. So this is kind of scenario 1. And now let's look at another scenario. And let's look at, again, 2 cylinders of a gas we have. But now it should be such that, and I mean, we go from here to here in the process, let's say. So we do the same process, but the difference, as you can see from the drawing, is that now these should be indistinguishable particles. So the entropy of an ideal gas of a certain number of particles should, of course, here be the same. So I could choose the reference points of the entropy such that this still has entropy SA and this has entropy SB. By the way, I should maybe always write here thermodynamic entropy, but okay, you remember that. Now in this scenario, I can also write down an entropy of this system. So what's the entropy of this system here? Does anyone have an idea? The same? Yes. Okay, it's the same as something.
Same as what?
Yes, exactly. It's the same as something we already have. So the question is the same as what? Okay, yes. So I heard the word additivity, so you would say it's SA plus SB. Now I could make a different argument and say that the calculation I did here, why should it only work? I mean, I never really used this is just 2 particles, and maybe I could even think here that I actually have labels at the particles, and so there's actually no difference. I just didn't maybe look very closely. So I could also argue that it's maybe the same as here, because I already did the calculation here. And why shouldn't I use this calculation? I could even gradually change. I mean, I could make these particles more and more indistinguishable. But the argument would always be the same. I mean, the argument didn't depend on how distinguishable the particles are. So I could also argue that I should have this here. So now we can make a voting. So who thinks that this is the correct expression? Okay, good. Who thinks that this one is the correct expression? Okay, at least someone. So the answer is that, okay, or before I give the answer, let me maybe make one additional or complicate things a bit. Let's now assume that these are really two different isotopes of the same chemical material. But let's assume we are now, I mean, I often make this example also in the context of hidden variable theories, but this is now a different context. So let's go back 120 years. So I think it wasn't discovered there are these different isotopes. So let's assume that actually what you're doing is the thing here on the right-hand side. You found two cylinders filled with gas, but all your chemical experiments show that they are the same gas because you cannot distinguish isotopes. So from your point of view, the situation looks as if you have as scenario 2. So that's a possibility. So then, of course, because it looks like that, you would probably do what now the majority of you was doing, namely to say that, of course, entropy has to be additive. So we are going for the first option. So in other words, let's say the experimentalist 120 years ago would thinks he is in scenario 2, and therefore he would conclude that the entropy is equal to SA plus SB. Maybe. I mean, that's one possible answer he could give, because a majority of you gave this answer for the scenario 2. Now, later this experimentalist, of course, may discover that he was wrong, and actually they are distinguishable. So the same experiment, so it's the same experiment we do. There's nothing different we do. We just put the two compartments together and open a wall. Analyzed today. So now we know there are different isotopes. So we clearly in this situation, here we did this calculation, would lead to S equal SA plus SB plus N. Okay. So you see, now the situation is more complicated because now I didn't ask about a different experiment. Here they looked like different experiments. But now I said it's just you have different knowledge. This is an analysis you did to the best of your knowledge. You took everything into account you could and came to that conclusion. And later you found that you were actually wrong. So, yes, there's the oracle speaking. Okay. Yes. Yes. Yes, yes. So what he's saying is that clearly this was just a wrong analysis because we didn't know that the particles are distinguishable. So then, but this would mean, okay, yes, okay, that's one point of view. So now let me.
When you combine systems, you're not actually combining the systems here. In order to combine the systems, you have to first double the size, then superpose them.
Okay, yes, that's also. So maybe before we discuss further, let me now give the answer that you will find in this paper that I referenced, which in my opinion resolves the paradox, this paper by Chains. So what he would say is that both answers are perfectly correct. You can, there's not one right and one wrong. But the difference is just that you look at them from a different perspective. So it's really this subjective point of view on entropy. So what do I mean that both are correct? How can it be that two entropy expressions are the same? So the point is that if you are an experimentalist in this scenario, and you simply don't know that, you have no clue of how distinguishing these particles. Then you can develop a theory where the particles are always modeled as the same. It's of course just a model, but you don't have a better model. And then your whole thermodynamic theory that you will develop will be completely consistent with everything that you can do using that technology. So in some way, you could say, as long as I'm ignorant about the fact that these particles are different, and as long as I stay ignorant, then my knowledge is always the same. So I have a consistent theory that is built on the fact that I have this ignorance. And I don't need to care that actually they would be different, but I didn't notice it. Because I never, so in other words, if I never do an experiment that actually distinguishes them, I have an absolutely consistent theory. And this, I mean, by correct, I mean, at the end, I mean, you see, correct, when I say both are correct, what I mean is in both cases you have a completely consistent theory. Now, once you discover a method to distinguish them, you are able to do additional experiments. And if you do additional experiments, then you could, for example, do the following experiment. You could mix them and then again insert the wall and then try to see whether you are back in this situation. If you do that experiment here without your knowledge, you will find that you're still back in the original situation. If you do the experiment here knowing that the particles are different, you will find that if you just again insert the wall, they will be mixed. You will no longer arrive at the same situation. So you cannot go back without doing something more elaborate. So in other words, if you now analyze the very same experiment, but based on additional knowledge, so that's the only difference. You do exactly the same experiment, but you have additional knowledge, then you would come to another answer, and the thermodynamic theory that you build up is also perfectly consistent with that knowledge you have. And that's exactly the situation we have also in information theory. So in information theory, I mentioned this example with a coin. So which answer was correct? The answer that I say the entropy of the coin is 0 because I know its value. Or is your answer correct? You would say the entropy of the coin is 1 because you don't know its value. In the same way as here, both answers are absolutely correct. And if you would further calculate things with this entropy, all the things you will derive from that would be perfectly consistent with your knowledge. What you are not allowed to do is during the calculation suddenly change your knowledge and say, now I suddenly assume that I know the particles are distinguishable. So as long as I fix the knowledge I have, this has to be fixed, everything will be consistent in both ways. So in that sense, both answers here are correct. There's a question, yes?
Yeah, well, what I don't understand, there was this initial formula, delta Q is delta S by delta T.
Yes. Mm-hmm.
If I apply this here, this would mean that the energy in the right picture changes. And in the left picture it doesn't. But
Yes. Mm-hmm. Yes, yes, yes.
So, but isn't energy something that is objective?
Yes, so that's a very good point. Yes, energy is absolutely objective quantity, but what changes is not the energy but the heat. It's the Q, not the E. And now, you see, if we now go from here, okay, let's say we do this thing, we go from here to here. So in both cases, we don't require any energy. We just take out the wall. And now, let's go back here. Now the experimentalist here, and that's why I insisted he should never change his knowledge. So he will always be ignorant about which particle is which. So he can really go from here to here and will never notice the difference. Of course, for this guy, he will notice, oh, this one made a mistake, but all his experimental devices will never allow him to distinguish whether the particles here are now here of one kind or the other. So he has to remain with, he shouldn't change his knowledge about the microscopic state. So he can really go from here to here, and in his view, this is absolutely correct. Now, this guy here, if he wants to go from here to here, has to actually unmix the gas with the process that I did. So unmix the gas means that he has to do something non-trivial. And so he has to insert, or he has to execute some work, but the work will be moved into heat. But so the energy of these two systems are the same, but so somehow the process that I was able to carry out was not the same. And maybe I should actually explain it in the other way around. So in some way, I should more explain it in the direction going from here to here. So in some way, of course, this guy has more knowledge, so he has an advantage. So when this guy goes from here to here, he cannot gain any work. He will just, the only process he can do is to open the wall and then it will mix. This guy here has more knowledge, so he can actually do the very process that I described, but in the opposite direction. So he can actually insert a wall, a membrane here, and let the membrane expand, and do this expansion of the gas, of this, so that somehow you can let the times gas expand and let the plus gas expand separately and gain energy from that. So now in this case, this guy didn't get any work. This guy here was able to transform heat into work. So at the end here for this guy, the process is of the form, so delta U is 0. So the thing doesn't change. That's true for both of them. But this guy here had also delta Q is equal to 0 and delta W is equal to 0. So he just opened the thing and nothing happened. This guy here is in a better position. He has delta W is minus NKT ln2, and delta Q for him is equal to NKT ln2. So this guy actually, I mean, a negative W means he gains work. So this guy could actually transform heat into work, and this guy couldn't. Of course, exploiting his knowledge.
I think what you're saying is if he has the knowledge to make the right kind of membrane,
Yes.
then he can burn
Right.
it down.
Yes. Exactly. Yes. Yes. So we had yesterday also this example with whether you burn your hand on a hot plate. This reminds me of that. So of course here it's similar. So if you have here additional knowledge which you can exploit to do something useful, and this guy by definition doesn't have this ability. So we are not making a mistake by making these statements, because the guy cannot do better. This is just the optimal reversible process for him is of that type. For this guy, the optimal reversible process has to be of that type. So because they have different knowledges, they have actually different processes, and the processes don't have any impact on the energy. So that's clear. So energy is something that is kind of objective in this, at least from that point of view, but they can do more, and so this illustrates that work, the amount of work you can gain via a process is clearly a subjective quantity, because the amount of work you can draw from a system depends on the knowledge you have about the system. So this guy has more knowledge, so he can draw more work from the system. This guy has less knowledge, so he can get less work of the system. But in both cases, everything is consistent.
The reason actually the definition of thermodynamic entropy
Mhm.
is only expressed in terms of change of entropy. There is no.
Yes, it's a change of entropy. So when I write here this, you see, I have here this SA plus SB. This could be chosen arbitrarily. So
Another way, I mean, the first one, identical particle case. Also, you can intentionally put the work.
Mhm.
You also dissipated the heat.
mhm.
You are assuming you are just manipulating, actually moving one particle and that particle.
Mhm.
You can still put some work.
You can always do, I mean, here it's important that for the definition of the entropy, we have to have a reversible process. So it's important that you always do the best thing you can do. So that's why in this case you have to do that process. You shouldn't just put some work somewhere which is dissipated as heat. But let me now maybe summarize that this is just an example, another example showing that even in thermodynamics, the notion of entropy is somehow a subjective notion, although this is often not made explicit. So, and if you now go actually to statistical mechanics, you see that even the notion of the number of microscopic states is in some way appears to be subjective. Of course, you could say this is the real number of microscopic states, but it could be that this guy is still lacking some knowledge. So somehow, if you want to interpret entropy as the number of microstates, you should be aware that it's only counting the number of microstates which are relevant, which are kind of in principle accessible in a process. So this guy would come to a different, so if this guy would now say that entropy should now be interpreted in statistical mechanics as the number of microstates, he would come to a different answer than this guy here, which is clear because he would just not distinguish certain microstates which appear to this guy to be different. He would just call them the same microstates. So there's not a, so the paradox in that sense is resolved. So it's not the problem that there are two different entropic expressions. Yes?
But this highly depends on definition of the entropy, right? Because if I could extend this whole phenomenon onto some other quantity, I would have to do over every paper, every experiment ever done as soon as I get some knowledge.
Mm-hmm. So the definition of so it's a good point. So of course, the fact that I get here different answers comes from the fact that this definition that we had, I guess it's probably still here. So this definition has to be somehow dependent on the observer, and it is because here we have a delta Q. So the fact this definition is always the same. What is different is the interpretation of delta Q. And delta Q is the amount of heat you can, in a reversible way, put into a system. If you have more information about the system, then it means something different. So this process here, from here to here, is reversible for that observer. So for him, the right quantity is delta Q equals 0. And for that observer, the right quantity delta Q is not 0. It's a different one. So the definition of entropy is the same. It's just that you have to be aware of the fact that Q is reversible. And what reversible means, that's kind of a subjective thing. So this process which is reversible for this guy is not reversible for this guy. But it's always the same definition of entropy. It's more like a distinction of yes, what the knowledge implies about which part is heat and which part is work. Yes?
Analysis works as long as we assume some sort of infinite reservoir with a finite temperature. Now, what happens if I have a reservoir with a finite temperature, and I look at the process from the point of view of the guy to the right,
Mm-hmm.
looks like we should conclude that, from that point of view, I see two different pieces of gas, and each of them is expanding.
Mm-hmm.
Expanding should lower the temperature. Now, I'm doing everything adiabatically, such as
Mm-hmm.
in thermal equilibrium
Uh-huh.
bath, I would expect the temperature of the bath to be lower.
Ah, yeah, so you're now asking what happens if, now I did everything in a scenario where I do isothermal expansion. So I'm assuming the system is always in contact to a reservoir and I do the processes slow enough so that the system is always in thermal equilibrium. Now, of course, I mean, this is just an example. And I could do a different example where I do the expansion adiabatically without contact to a thermal bath. And of course, the actual then I'm comparing, this system will then be cooler than that system. So I have to, I'm comparing different systems then.
Even without knowing that the particles are different for measure the heat. So let's assume that the bath is the same for both.
Mhm.
Now the guy to the right will conclude that the bath should lower the temperature if it's finite bath. And the guy to the left will not conclude. So
You're saying if you could measure how much you could measure the amount of heat that goes into the bath and then see that there is actually an objective difference. Yes, that's true, but you're actually really doing different processes. So it's not that the two are, so because they have different knowledge, they also do something different. So, of course, if this guy would now observe what that guy is doing, he would see, oh, this guy has obviously kind of more sophisticated techniques and can do something which looks magic to me. Like if you don't know that there are different particles, but you see some guy always being able to somehow distinguish them, then you would not be surprised that this guy can now do something better and maybe heat the reservoir that you are not able to heat, or cool the reservoir.
does it make sense that the guy to the left will learn that the particles are different by measuring the temperature outside?
So if this guy would observe that experiment, he would learn that the particles are probably different.
But in the experiment just described, there was no particular knowledge used, right?
No, it was. This is a very good point. I forgot to say that. Yes.
There's a thermometer
Yes.
in the heat part,
Yes.
and then we remove this membrane that is isolated
Yeah.
for everything. So this is an experiment anyone can do.
This one. This is this experiment.
On the other side,
No. Actually, to do that.
use the special membrane for that.
No, for that to do that with that particle W and that Q, you need the membrane. because you would do the process that I described at the beginning, the one that is maybe partially still here, this process here, I would do that in reverse. So I would somehow let this gas expand with the membrane. So I would first insert the membranes here, and then put the cylinders together, and then let the membranes expand.
So you say that actually this arrow down there, it's like essentially the maximum work I can get,
Yes.
but I can choose to get less work than I'm
Yes,
allowed.
but you cannot choose for the definition, because the definition...
You can choose for the heat that I measure with the thermometer.
Yes, yes,
So the
yes.
node difference can choose to not work.
Yes, he can choose to not do an optimal thing, but the definition of entropy requires you to do the optimal thing. That's why he would not, I mean, just for the calculation of S, he would not be allowed to do anything else. There was another question there. Okay, okay, good. Okay, so this was just now supposed to be an example. It took a little bit longer than I expected, but I think it's maybe important to see that point. Now, let me come back to the techniques we had. So maybe you remember that I introduced this technique of decoupling, which we are now going to use to establish a connection. So our goal is still to somehow make it more specific. I'm always announcing that there is somehow an analogy between, but this thing is not proved yet. And so how would people argue in statistical mechanics? So in statistical mechanics, there are different ways to argue that they are the same. One way is, for example, to just calculate the entropy of an ideal gas in the formalism of thermodynamics, and to calculate the entropy of an ideal gas in statistical mechanics. And then you get the expression that formally looks similar, and then you say, because they look similar, the entropy, this quantity has to be somehow related to the other one. So that's somehow what you do. So it's somehow a comparison where you at the end say, because for the same system, for the same physical system, using completely different theories with completely different types of variables and definitions, at the end you find the same formula, then these objects somehow have to match. That's a pretty standard approach to argue why the two things are similar. There are also other approaches which are more information theoretic, and that's now, of course, what we would like to do. Okay. And the decoupling is needed to do that, or needed, at least it's one way to do it. So let me briefly remind you of this decoupling statement. So the decoupling statement tells you the following. You've seen that yesterday, but maybe I draw a simplified picture. You have this system A, which consists of n qubits. And now there is some unitary U. And then you look at the system which is somehow separated, where there are k qubits here and n minus k here. Okay, this is the system A prime and A prime prime. And there are k qubits here. And then you discard that thing. So you just throw that into a bin. And you're somehow asking now, so if you're now only looking at these A prime qubits, how well are they correlated to some other system? So you have this reference system R, and there's somehow a correlation between R and A, which can be arbitrary. And now you're asking how well are these things correlated? And as I said, the goal, I mean, what we would like to have typically is to have a situation where the state here after, maybe in contrast to last time, let me write here the unitary to just make explicit that we're talking about one fixed unitary. But at the end we cannot have a theorem about one fixed unitary. But the scenario, I mean, the physical situation is just talking about one fixed unitary. There's no randomness in it. The randomness is only kind of the weakness or the lack of a better statement that has to introduce some statement about sets of unitaries. But in the physical scenario, it's important to distinguish that. There's the physical scenario we want to talk about, and there's a theorem which is slightly weaker than what we would like to have. So the physical scenario tells us that this rho, would require us to show that this rho U of A prime and R is essentially a mixture of, maybe I write it this time like that, A prime tensor rho R, where this thing here is a maximally mixed. So that's what we want, and we want to have this to be true to good approximation. And the theorem that I called the decoupling theorem is telling you the following. It's telling you that this goal, so we consider, maybe I look at it like that, we have, let's say we have somehow some set of unitaries, so which I call sigma. So this is a set of unitaries. And the theorem tells you now for certain, of course, there will be different parameters for different sets. But for most u element of this thing, the following holds. Or for most, well, I say it's more easily. For most u, the goal, which is described here, the goal is achieved, or decoupling is achieved, if the entropy of the initial thing of A given R is larger than something, namely larger than 2k minus n. And now the theorem is proved under different constraints on sigma. So that's why I didn't specify it. But the original proof applies for sigma, where sigma is the set of all possible unitaries, and most means almost all in a measure theoretic sense when you take a unitarily equivalent measure or a Haar measure over this set. There are better theorems where this set is much smaller, where this set is, for example, only those unitaries that can be achieved by just a few two-body interactions. And then this statement is still true with slightly different parameters. I mean, there are some, here is something which is kind of, I mean, this is approximately true, and I told you that there is some additive constant log 1 over epsilon, and if you have smaller sets, there may be additional weakenings of that statement. But the type of statement is always that if the entropy is sufficiently high, then you get that. Of course, if this set is too small, and that's why this was also a question that John asked yesterday. So, of course, what we would like to have is here just a set that has one element, namely the actual physical U that's happening. For example, if you apply this thing to thermalization, and you were asking me why does a cup of tea thermalize, then there's one particular U that describes what's going on in this cup of tea. It's probably time-independent U. And so what the theorem that I would like to have is one which would say there is this set of unitaries which has only one element, namely the unitary that describes the cup of tea. And then it would say, if I apply this unitary, and then at the end it thermalizes. I will go more into why this means thermalization later, but that would be the statement. Now, unfortunately, here is A given R. So this is about the initial state. So we are asking what is the condition on the initial state so that we get thermalization. So unfortunately now, the best theorems we have are such that this sigma set is still relatively large, but not so large as to contain all unitaries. So, and the goal maybe in research should be to make this set sigma smaller and smaller so that it only contains the actual unitaries that we know are actually physically realized. Yes? Yes, but yes. So because, of course, if this was only one particular element, it would matter. But because U is usually chosen from a relatively large set, it doesn't matter so much. Yes?
So you're, I guess the way to phrase it is, does the set of U such that this goal is achieved, that I suppose depends on the initial state? So if you wanted to say something about it.
Yes. So the type of state, I mean, of course, one would hope that we can get a stronger statement if we make it depending on the initial state. But these statements, as they're formulated, now hold even if you don't depend on the initial state.
You're randomizing over U to sort of
yes. So because we are randomizing, we get a benefit. We don't have to fix initial state. If one wants to strengthen the theorem, I mean strengthen in terms of making it. If one wants to make the set smaller, one may have to give up the independence on the initial state. That's absolutely correct, yes. Let me also say that this theorem is almost tight. And by almost, I mean, again, up to certain log 1 over epsilons. And tight means that even for any unitary, so there cannot be a unitary that achieves that goal if this condition doesn't hold. So this condition is really necessary, which also tells you that this measure here, this entropy measure, is actually the right measure. I mean, if it wasn't tight, you could say this is just some maybe weak condition. But because it's tight, it tells you this is really the thing that tells you how well you will be able to decouple. And because this theorem now tells us that this is the right measure, it's now probably time to have a small side where I tell you what this thing is. So this object popped up many times also in Michał Horodecki's talk. There was also something called H max. And he also introduced it, but let me here introduce mostly this H max. And so I would like to briefly focus on the H min. I will make that very short because actually it's not necessary that you understand the details of how this is defined. There are only certain things you need to know about it to understand what's going on. So first of all, this is called a smooth entropy, and smooth, this term smooth will just be clear in a minute. Now I have to choose where to write. And these smooth entropies are not only used in thermodynamics. I mean, they pop up everywhere. And for example, in cryptography, but also in communication theory. And what we will see in a minute is that these smooth entropies are in a strict sense a generalization of the von Neumann entropy. So roughly speaking, what we will see is that, or maybe I should first mention that if you read any information theory book, like Shannon's work, or this Thomas Cover, which is the classical textbook on information theory, you will always find that all the results are expressed in terms of Shannon entropy or von Neumann entropy. So you would somehow conclude from that this is really the universal measure of entropy that should be used for everything. And indeed, some people are assuming that and are starting to define other quantities based on entropy, just based on the reason that this entropy measure is already used often. So, I mean, this may be a dangerous remark, but I would say people, for example, who define things like what they call discord, just took a measure of entropy but didn't know why, and then defined a new measure based on that. But it's not clear why one should take the von Neumann entropy. I mean, they took a mutual information which is based on the von Neumann entropy. And indeed, if you now ask yourself why is it the Shannon entropy that is relevant, then the answer that you will find is the following, and I hope I can clarify that answer in a minute. The answer is that in information theory, it's almost always an assumption that you make that you are looking at scenarios where you have many independent repetitions of the same process. So my PhD supervisor, Uli Maurer, who is an information theorist and cryptographer, once said, this is an assumption that is just hard-coded in any information theorist's brain. They wouldn't even start thinking about a scenario where you don't have many independent repetitions. It's probably not true to that extent, but if you look at these textbooks, you will find that all the results which at the end lead to the Shannon entropy have that property. I mean, there's some weakening. You can use some Markov property to slightly weaken that, but essentially results are only true if you make that assumption. And now this assumption is, of course, perfectly fine in communication theory, because indeed, if you use a channel many times, the channel will, to good approximation, have the same behavior each time you use it, roughly. I mean, this is, of course, an approximation, but obviously, or as our technological advance shows, this is a very good approximation. But in physics, we are kind of in a different scenario. In physics, if we are asking questions like how much work does it cost me to erase that blackboard? This is clearly not an IID process, because I'm not erasing asymptotically many blackboards which are independently distributed. I'm just somehow erasing one. And in particular, I don't erase them at the same time in parallel, because I would need that in order to make such an argument. So in physics, we typically have one system that we consider, or one solid state. And so it turns out that in this case, the Shannon entropy is simply not the right measure. And nevertheless, it's a very good measure. But, okay, that will now be clear, I hope, in a minute. So let's first start with this particular measure. So I first just give a definition, which will probably not give you much insight why it's useful. But so first of all, I can define it in terms of, so I make a simplified definition which doesn't have an epsilon. and no conditioning. So in this case, the mean entropy is just defined as minus log the maximum probability of a probability distribution Px. If I do the same thing for quantum states, I mean, I could also define the same thing for a quantum state, then what it is just, this is kind of the same thing, just written for a quantum state. So this infinity L, this L infinity norm is just the maximum eigenvalue, and you take the negative log of that. Now, if you think about this, you can always interpret that as somehow what some people call the guessing probability. So it's the probability of the largest probability is always the probability with which you would correctly guess the value. So if I have, for example, a probability distribution, so if I have a probability distribution, I have here two values, 0 and 1, and one value has probability 2/3, and one has probability 1/3, then clearly if I ask you, please guess what outcome I will obtain if I do an experiment that will give you an x distributed according to that, you will guess that it will give the outcome 0, and you will be right with probability 2/3. And that's exactly this quantity here. So it's very simple. Now, if you add the conditioning, it's actually the same intuition applies. So the notation is a little bit different, but let me now assume for the moment that x is some classical value and b is some arbitrary quantum system. So this would be a so-called classical quantum state. That's still not the most general thing, but I will come soon to the most general thing. So this would be, let's assume the state is of that form. So the state has some probability distribution over orthogonal states x, these are the classical values, and some quantum state on the system B, which may depend on x. And now the entropy in that case would again be minus log 2 of the guessing probability of correctly guessing x if I know B. So formally, what is that? What is the probability of correctly guessing the value x if I have access to B? I can write that down as a formula if you like. One way to write it is this way. This is not so important. It's just maybe to make clear what it is. So I maximize over all possible POVMs on the system B and label them the family, or have an index labeled with x. And then I carry out a measurement according to this POVM on the state. This is always the state of x and p, so I carry out the measurement on that state. And then I look whether the outcome is x. So somehow it's like carrying out the measurement on b and making a guess for x. And now I do that, I optimize over all possible measurements. And of course, if I have the best measurement, this is the best strategy of guessing x. So this is just a way to write formally what it means to try to guess a value x if you have access to a quantum system B, and try to maximize your probability of correctly predicting what the value x is. You can think, you can easily verify that this is that thing. Okay, so these are all definitions in special cases, but they show you that somehow this measure has the intuition of being a measure that tells you how likely certain values are. It's clear that the probability of guessing something is related to how uncertain you are about the value. So in particular, if you have, for example, a uniform bit, then clearly the probability of guessing it correctly is 1/2, so the entropy is 1. If you know it perfectly, the probability of guessing is 1, so therefore the entropy is 0. And so this is kind of a concept that generalizes that. Okay, now let's move on and say, yes, there's a question.
Tell us also the formula for the classical conditional entropy. That might help us understand.
Yes, so yes, okay, that's a good question. Let me write down the explicit formula for the classical conditional mean entropy. So it's again the guessing probability, because this is just a special case of this thing. So if I have a classical probability distribution Pxy, then I can calculate the mean entropy of x given y. And one way to write it is the following way. So it's again this minus log 2. So you see there's always a minus log 2. This is, somebody could say this is just a convention because it's always a log in front of the whole thing. And we want the entropies to be additive. So this is just because of that. And now you could write it as that. You could say that it's the I first sum over y. I mean, there are different equivalent ways to write the same thing. And then it's the guessing probability p guess of x, of the probability, so of x given that y is this particular y. So what is this? This is the maximum over x of the conditional probability distribution of x given y. So in some way, you could see like the guessing, the probability of guessing correctly in x, if you have access to y, is somehow the average over the probability that you're guessing x correctly when you know y, when y has a specific value, averaged over all possible values of y.
The averaging is inside the log.
Yes, that happens to be the case, yes. That's an important difference. So this entropy is not an average over mean entropy is conditioned on that. Yes, that's important.
But in the quantum case, you had a sum over x.
Yes, okay. This was just a different, I mean, I could also write that in that form. They're equivalent. Here, you see the maximization is kind of turned into a maximization over POVMs. And it turns out that this maximization over so because, for example, if one x I would never choose would just mean that this particular element in the POVM would have weight 0. So I mean, would not occur. But it's I mean, I don't now want to show the equivalence, but it's relatively easy to show. It's not complete. I mean, one has to think maybe for 5 or 10 minutes how to transform it. But the important thing is to realize that the maximization comes in via the choice of these x's, which somehow then influence how. So certain x's will never occur because you just the corresponding e operator would be a 0 operator. If you want, we can discuss it later, but it would take a little bit more than 5 minutes to actually do it properly.
In the classical case, why do you sum over y rather than take the max over 1?
Why? Okay. It's a good, I mean, you could, of course, ask the general question, why is it defined like that? Maybe let me come back to that. I mean, of course, I could have written now anything, and of course, there's a reason why it's like that. But let me now finally give the fully general definition, which also involves maybe first without the epsilon, but for an arbitrary quantum state. And it's so this definition is that it's the okay. Now I have to write it in such a way that I will be consistent with my. So I do the maximum. I mean, there are different ways of first writing the minus and then a minimum, or doing it that way. But let me do it in that way. It's the maximum lambda such that rho a b is as an operator smaller or equal. So this looks now a bit scary. 2 to the minus lambda. It's not done yet, but I need to have some more space. And I mean, you will see, I will argue that it's not so important at this point to understand what this thing is. It's just important that you know that there is a definition. So, okay, it's not obvious to see why this should now reduce in the classical case to that. So this is really not obvious. You need some semi-definite programming and then some duality relation to make the connection between this and what I told you before. So the idea why I gave you those is that these special cases are kind of intuitive. Here you somehow have an intuition what it means to guess a value. Why this should, whereas this definition somehow involves operator inequalities, so it's not clear what they mean operationally. But you can show, and this is now just a theorem I cite. So it has been shown by Robert Koenig and others that this definition is equivalent in these special cases to all those definitions here.
Is there a norm or something somewhere there? I'm not used to seeing just declaring the operator is less than another operator. No, what that means, so if I write an operator P or an operator
P is smaller than operator Q, I mean that the operator Q minus P is non-negative. So what I mean is that if you would subtract that, then you get a new operator, and that's a non-negative operator.
This might be hard to compute.
Yes, okay, that's another point. This might be hard to compute. It turns out that it can be efficiently computed. There's some, it even has been programmed. So the point is that you can all do with semi-definite programs, and semi-definite programs are efficient. I mean, efficient in a computer science sense, but also it's kind of quadratic in the input side. So of course, it soon gets uncomputed because usually density operators are very large, but that's also true for all other, I mean, usually the problem is that just the density operators are large to compute any entropy. But if you can compute an entropy, then you can usually also compute that entropy. You don't, actually the nice thing is you don't even have to diagonalize or so. So in contrast to the, let's say for Neumann entropy, you don't have to take a logarithm of a density operator, which saves you a lot of time. Because if you want to compute a logarithm of a density operator, you have to, or I don't know another method than diagonalizing the density operator, which is quite computing or quite resource consuming. Yes?
Just to be clear, what does it mean that the operator is bigger? Formally, what?
Aha, yes. So, sorry, maybe I should really have it. So this, what I mean, so this was already the answer before. What I mean is that if you would subtract both, so there's a new operator that would be, so you could somehow rewrite that as this. So there's an operator here and an operator here. So I can subtract that operator from that. And then this gives a new operator. And so this means that this operator is non-negative. So that the operator is non-negative means all its eigenvalues are, for example, non-negative. Okay, and the point is, and I also don't explain that here, that this can be efficiently computed, but this is also not that important because you usually never compute this quantity directly. What you use them usually in proofs for very large density operators, which you anyway cannot represent, and then at the end you show some property of that, but you usually never have to compute it. So it's not particularly useful to think about how to compute it because it never occurred to me that I actually had to compute it. Now there is also the smoothed version, and the smoothed version has is just defined in the same way, except that. Oh, sorry. I realized I made a mistake. Here, this should not be. This is not the marginal of the operator. This is some other some arbitrary density operator sigma b. So the optimization is over all those. And this actually makes it easier to compute it, because you do it via semi-definite programming. The dual program of that will become easier if you have more variables to optimize over.
The max is now over both lambda and sigma?
Yes, yes. So you take the maximum lambda such that there exists a sigma b such that this holds. Yes.
Oh, okay.
So it's somehow the maximum is over both, but you take the value of the lambda.
Sigma b is a density.
Yes, it's a density operator. So there exists a density of, this is a density operator, yes.
And the physical meaning is still the same? It's the best guess you can get for
Yes,
A to
yes,
measure B?
yes, yes. You just have to ask what does it mean to guess the quantum value. But it has a meaning. You can, yes. So, and now there is this smooth version, which is doing almost the same, but you're kind of talking about a density operator AB prime, which is supposed to be smaller than that, where the AB prime is somehow close, epsilon close to rho AB. Okay, so this is maybe all a bit confusing. There are lots of definitions. At the end, it's just, this is the actual definition. I just built it up from smaller parts, but this is at the end the definition of the whole thing. Okay, but as I said, you don't have to worry about the definition, because what we worry about are more the properties of that. Yes?
I'm just curious, is it just a historical reason that it's not defined in terms of the dual?
You can also write down the dual.
Because that's maybe a bit, I think it looks nicer because it's program equality.
Yes. So there are, yes, I mean, it looks nicer if you don't do the smoothing. If you do the smoothing, you have a minimization and a maximization sometimes. So it's, yeah, it depends on, I mean, it's a matter of, so there are many equivalent ways to write that. That's right, and it's a matter of taste which one is better. I'm not necessarily arguing this is the nicest one, because I don't want to argue about which formula is nicer than another one. It's one, but what I want to argue about is that you don't have to worry about that at the moment so much, because what I will show you is that what we will need are the properties of that. And once you have proved the properties of this measure, you never have to go back to the definition. Because as I said, I don't have to compute the explicit value. Of course, when you prove the properties, you have to worry about the definition. So we will still need it for a moment, but then once we know the properties, we can completely forget about them. So let me now write down two properties of that. So, okay, now I need to briefly check the time. Oh, it's already, okay, so I have to hurry up a bit. So let me give you, or tell you now that maybe so entropies usually have properties that should be natural. For example, entropy is concave. I mean, that's what you learn in thermodynamics. Now, for this conditional entropy measure, there's something more subtle that holds, but more intuitive in some way. It's called the data processing inequality. And one could argue that any entropy measure should have that property. So what is the property? The property is the following. It tells you that H min epsilon of A given B C is smaller or equal to H min epsilon of A given B. Why is that natural? So if you remember the definition of, or the intuition about the entropy is that the entropy should tell you how uncertain are you about A when you have access to this. But clearly, you should be less uncertain about A if you know B and C compared to a situation where you only know B. So in other words, what this thing tells you is that your uncertainty cannot decrease if you forget something. That's very intuitive. I mean, I think it usually doesn't happen to you that you forget something and then you're more certain about something. So, yes, maybe everything can happen. Yes, okay, but for entropies it shouldn't be the case. Okay. Now let me stress that for the von Neumann entropy, this was something that was very hard to prove. There was actually, it took several years. I mean, this was before my time in quantum information, but from what I've seen or talking to people who worked on that, like Mari Petruskaj and Lieb, this was kind of non-trivial to prove. However, I will now show you a two-lines proof that this is true for this entropy measure. So we'll see it's actually quite easy. Yes?
So basically, that should be like a comma between the B and the C, like it's two different sizes. They don't depend, it's not some multiplication or something.
A comma between what? Between the
What do you mean by BC?
Ah, yes. Okay, what do I mean by... So these are just two systems that I consider as one. So yes, maybe I should have clarified. And so what it means is that I have somehow a system A, a system B, and a system C. And now first I'm asking the question, taking these together, that's what this BC means. How uncertain am I about A if I consider all knowledge stored here in these systems? And then I forget one. So here I look at the situation where I only have A, and I got rid of C. So I'm now asking how much knowledge do I still have left about A once I've forgotten C? Now let me briefly give the proof. So maybe you see it directly from the definition. So the proof is, I just need to write down essentially the definition, and then the proof is almost there. So what does the entropy in general tell me? So the proof is the following. Of course, if I have the maximum lambda, if the entropy is defined as the maximum lambda, I can just write down this inequality that I have here, A, B. So now I have to write it also with the C system, of course. So, because now B consists now of B and C. So what this inequality tells me is that this operator is smaller than 2 to the minus H min epsilon of A given BC times the operator identity A tensor some operator sigma BC. So that's directly what the definition tells me. I mean, I've not done anything. And now I do something trivial. I just take on both sides the trace over C. Now you can easily verify that if an operator inequality is true, and if you trace out one subsystem, then it's still true. So this just follows from the fact that if an operator is positive, and you trace out a subsystem, then it's still a positive operator. So this immediately implies that rho prime AB is still smaller than 2 to the minus h. Here I don't change anything. So it's still A given BC. This is just a number times IDA. And here I've traced out C. But of course, this is still a valid density operator, sigma B. And now I'm already done, because now I can just, again, read the definition. And the definition tells me that what this should be is the maximum lambda such that this thing is true. So I'm somehow looking for the maximum. Let me maybe use a color for that. So I'm looking for the maximum lambda. So the lambda should be here, such that this holds. But I've already proved this inequality, that the inequality holds if I set as lambda this. So the maximum lambda can only be larger than that value here. And that proves the theorem. So in other words, I have here a maximization problem, and I'm just observing that I've already satisfied the condition of the maximization problem if I insert this. So clearly, there is the maximization, the maximum value has to be larger than this one. And this is what the statement says. So the proof is really trivial. So you see, the definition is actually, it looks a little bit scary, but it's very different. What you have to observe is that, of course, if this thing is close to rho IBC, then, of course, this thing is still close to rho AB, but that follows from the monotonicity of the distance measures. Okay, so that was the proof. Now let me finally come to an important statement that explains what I told you before, namely that the von Neumann entropy is somehow a special case. And this is a consequence of what people call the asymptotic equipartition property. And this is something you can also prove yourself in the problem set. So this is one of the problems, but the problem is for the non-conditional version, and more precisely for H max, which I will mention in a minute. So the statement is the following, that if epsilon is larger than 0 and smaller than 1, then the following holds. If I take H min epsilon, and I now look at, instead of a quantum state rho, I look at an n-fold tensor product of a quantum state rho, but divide again by n. So in some way, you should think of, I have a system A1 and a system B1, and I have a system A2 and a system B2, and so on, until AN and Bn, and they're all in the state rho. Each system, they're all independent of each other and in the state rho. So this is now the IID case. This is what I said is the fact that is hard-coded in all information theorists' brains, that the world is like that. The things are independent. And now I can calculate the entropy of these things, AN given Bn. So I calculate how much uncertainty we have about all those, given the knowledge stored in all B systems. And I normalize that by n, because of course the entropy is kind of additive, so it grows with n. And now I look what happens if n goes to infinity, and what I will find is that this goes to the von Neumann, to the conditional von Neumann entropy of A given B. So in other words, the von Neumann entropy is in a strict sense one particular value of this smooth mean entropy, namely if you evaluate the mean entropy for IID states. And this explains why there is not a contradiction. I will now argue that this is actually in scenarios where you don't have the IID assumption, usually the right property. This one or the converse, which is H max. So this is whatever you do in single shot, whatever I've done and whatever people have done, you always find that it's this quantity. Whenever you have a tight expression, you see that it's this quantity. And that actually answers the question, why is it defined like that? It's defined like that because it turns out that in all operational settings that we considered so far, it turned out that this is actually the answer to the questions, whenever there's kind of an entropic answer and you don't look at the IID case. And now you could say, this contradicts what Shannon said, because Shannon always obtained the Shannon or von Neumann entropy. But it doesn't, because the Shannon entropy is just a special case of that, exactly in the case which he considered, which was the IID case. So in other words, if you take Shannon and his answers and say, let's give up the assumption that everything is independent and repeated infinitely often, then you will find that this is now the measure you should use. And so, by the way, this gives you a very nice proof so we now just prove this thing here. Where was it? Oh, that's the data processing inequality. Of course, this implies that everything that is true for this measure is automatically true for this one. So you somehow get as a benefit, I mean, this is of course not a trivial statement, but what you get is that you can now say, because of the data processing inequality, the data processing inequality holds for any entropy. So in particular, it holds if you have n copies of a state. So this must also hold. So that's just the data processing inequality applied to the special case of an IID state. Sorry? Oh, sorry, yes, thank you. Of course, this was in the other direction. So here it's important that there is that sign. And now I normalize it. That I can, of course, do on both sides. And now I take the limit, n going to infinity. And now, according to this asymptotic equipartition property, I get here the von Neumann entropy of A is A given B, C. And on the right-hand side, I get that. So you see, this is one possible proof of the what people call also strong subadditivity, based on actually something which is not so hard, namely this data processing inequality here. Of course, this thing is not completely trivial. So you still have to work somewhere. Pardon? So you still have to work here. But to get an impression of how this works, you can look at the problem set. And the problem set, in the problem set, you do this for the max entropy. Now I should probably briefly tell you what the max entropy is. So the max entropy is just the following.
Does the name H-min suggest that there is some relation, inequality between this and the von Neumann
Yes,
entropy?
yes, I will come to that. It will be smaller than the von Neumann entropy. So there's, for the von Neumann entropy, you can do this as an exercise. The following. If you have a state that is pure, then you will find that the von Neumann entropy of A given B is equal to the von Neumann entropy of A given C, but with an opposite sign. So that's something you can verify. Now, what we define is we define something which is the max entropy, which is A given B, and this is defined as minus the mean entropy of A given C. So in some way, for this statement, which is true for the von Neumann entropy, is no longer true for the mean entropy. So it's not the same whether I condition on B or whether I condition on C. But it gives me a new entropy measure. And now what turns out to be true is that the H-min, maybe explains the name, is always smaller than the von Neumann entropy, which is always smaller than H-max. And in fact, you can even show that every reasonable entropy measure, where reasonable means that you have an entropy measure satisfying certain natural conditions, like concavity and so on, will be in between H-min and H-max. And now what I said before is not entirely true. Or actually it's true, but always with respect to that. So I said, whenever you look at a scenario in the non-asymptotic case, you will find that the answer is H-min. But it may also be H-max, but because of this relation, it's actually essentially the same. It's just a matter of how you formulate it. Okay, so now, why did we do all that? So the point is that the decoupling theorem tells you that this is the right measure to measure when a system decouples. So if this entropy is large, then a system thermalizes. Now, okay, there will not be time to go into a proof, but let me nevertheless explain how this, what we all did all here, connects now to thermodynamics. So maybe I just give a very short, intuitive statement rather than a full proof of the following thing. So when we had this Landauer erasure principle before, or I mentioned that. So I mentioned that if we erase, so erasure of 1 bit costs kt ln2. And as I would also like to refer to the exercises where you derive that for a specific model. Now let's assume that we have some random variable. Let's now do the classical case. We have some random variable x, and the question is, how well can we erase that? So we want to erase it. We want to put it to 0. And the question is, how much work does it cost us optimally? Now, I told you already yesterday that we can do better than, of course, we could count how many bits do we have here, and then erase all these bits. But this will not be an optimal process. There's namely a more optimal one. What we could do is to do what people call compression, data compression. So whenever you have a random variable x, a classical random variable x, you will find that you can compress the x into some smaller value, some code word c, where c is usually smaller than the number of bits of x. So you can compress a huge movie onto a small DVD. And it turns out that the size of that is actually h max of c. Maybe I've learned that it's the Shannon entropy. But this is, of course, again, only true if you would be in the IID scenario. But if you're not in the IID scenario, so if you compress something once, then the answer is that. And this epsilon corresponds to the probability of failure you're tolerating.
H max of x.
Oh, sorry, yes, of course, otherwise it doesn't make sense. Thanks. Now, in some way you can use, so this is, okay. Now if you compress that to c, and c has only this size, you can of course apply this erasure here only to this part, because you see, if you compress something, then because compression is by definition a reversible process. I mean, if you want to compress something, you mean that you can again recreate x. But if this is a reversible process, it means that this process here can somehow be implemented by a unitary. And unitary doesn't cost any work. That's also one of the assumptions that we discussed yesterday. Here you need some work, but here you now have only so many bits. So the work you require here is only c. So c would be, okay, this what I mean here is number of bits, not the dimension. So it would be c times kt ln2. And so you see, I only have to erase a small part. And so what I have to erase, so the total work is therefore, I just insert this formula, h max of x times kt ln2. And now, this was just a classical intuition. Now, of course, you want to do these things for quantum systems, and you want to do it if you have some, maybe in general, some quantum information about them. And for that, you need decoupling. And what I will now not have time to show, but which you just have to believe me, is that decoupling is kind of giving you the quantum mechanical generalization of compression. The idea is essentially that you use something, I mean, you can use decoupling always, people call that in a dual way. So decoupling seems to do kind of the opposite of what you want. It creates something which is completely independent. But in quantum theory, of course, if I have a system A, which is completely uncorrelated to a system R, then at the same time, if I look at the purification of all that, I know that A must be perfectly correlated to some system B. So although decoupling sounds like a statement about systems that are independent, here I'm actually interested in systems that are perfectly correlated somehow. And so what you now just have to believe, I don't even attempt to give an explanation of that given the time, is that if you go to quantum mechanics, what you have to do is to replace this here by decoupling. And what you will find when you analyze everything in terms of decoupling is that the expression for the size of the systems will be of the following form. So what you will find is that the size of the decoupled system is, so now do the quantum version in blue, is minus h min of the system you have conditioned on E, where E is the whole environment. And there's some epsilon here. So you remember in the decoupling there was some h min. However, and here in the classical result you had some h max, but now it's just this relation which will actually give the h max. because now using this relation, we can of course rewrite this as H max epsilon of x conditioned on everything that purifies the environment. But the environment is already the purification of everything else. So what we have here is just the thing that is not the environment, which is kind of the device that carries out the erasure. So somewhere we have a system that has knowledge about x and tries to erase it, and we call that D, if you remember from last time. So it turns out that you get this formula, and the rest of the argument is the same. So this is now a very short summary that tells you how decoupling explains comes in here. But this is maybe now more advanced. So let me just use maybe 2 more minutes to give you a summary of what we did, rather than go into more details. So what we did is the following. We looked at processes where we looked at thermodynamic entropy and information theoretic entropy. And now what we have found, and this I didn't now explain in detail, but the formula one finds is that the relevant quantity for the work you need to erase a system is H max times this. Now what does this tell us about thermodynamics? Now I can make a very short argument. I can do the following. So what we proved here on a more abstract level is the following. If you have some x, some system x, and we have some, there's always this thermal bath we should think of. So there's always the process in somehow with respect to a thermal bath, and we have some device D, and this device D carries out an erasure process, brings the system back to 0. And this requires some work, and what we calculated is that the work that we need is kT ln2 times the max entropy of x conditioned on the knowledge of the device. Now, if we do such a process, we could require that the device after the process should be again in the same state as before. That's natural, because in thermodynamics we always look at cyclic processes, which means that the total energy of this transformation should be 0. So the energy of the system shouldn't have been changed. So this was as before. So we require that the delta U is 0. This is like it for the things we did before. But this means that the heat that is produced in this, so if I put here work into the system, it means that there is also some heat, which is minus the work. So I can now calculate the heat, but the heat will just be Q, will just be minus this thing. It's kT ln2 times H max of x given D. So this is the heat produced in a process where I erase a system, so where I reset the system from here to here. And now let's look what that tells us for the thermodynamic entropy. So the thermodynamic entropy can always be set, so the 0 point for the thermodynamic entropy can be chosen arbitrarily. So I could say that let's define that the thermodynamic entropy of a system that is in a pure state, this is just a 0 state, is 0. And now I can calculate, and I'm interested in the thermodynamic entropy of this thing. This is an arbitrary system. So what's the thermodynamic entropy of this system? Now I use the formula from thermodynamics. And the formula from thermodynamics is this famous formula that we use now many times, namely that the entropy change, so the delta entropy is equal to the change of Q divided by T. I now wrote the big delta because it's the whole process. Now so the delta S is kind of the final entropy minus the initial one. So what I have here is kind of minus, is minus STD. So this would be STD prime. So that's this, that's the final. The final is 0 minus the initial one. And on the right-hand side, I have this Q. So this is minus kT ln2 times H max of x given D. And I have to divide the whole thing by T. So the T cancels, and the minus also cancels. So what I find is that the thermodynamic entropy is equal to KT, the T cancelled, K ln2 times H max. There was always an H max epsilon of x given d. And this is the relation we have, I promised at the beginning. So we now have a relation between the thermodynamic entropy and the information theoretic entropy. And what we found is that in a setting where we don't have repetitions and no asymptotics, the thermodynamic entropy should actually not correspond to the von Neumann entropy, but to this max entropy. And because everything that I did was tight, we don't have actually an inequality. I didn't show why it's tight, but it turns out that this is tight. So why is it still correct to say that usually when people use here the von Neumann entropy in statistical mechanics, they do the right thing? This is again because of the asymptotic equipartition property, which is often also satisfied for things like gases. If you have a gas, it's kind of safe to assume that each gas particle is somehow, to a good approximation, independent of many other gas particles. So it turns out that in many relevant cases, so for large systems, for typical large systems, this is the same as the von Neumann entropy of x given d. So that's one thing we learn. So there are two things we learn. One thing is that it's actually a different entropy than we expected, but in the usual cases that we have physically, it still happens to be the one we expected to find. But actually, in general, it's not that one. The other thing we learn is that we have now very explicitly this subjective character in the theory. So the entropy is really the knowledge we have about the system conditioned on the knowledge we use when we operate on the system. And then this brings us back to this Gibbs paradox, because you remember this was very important that I said it depends on how much knowledge we have about the system in order to decide which operations we can apply. So this device that acts on the system comes in very explicitly in the information theoretic consideration, and it turns out that it has to be, even if you make the connection to thermodynamics, it's still there. So the thermodynamic or the information theoretic analog of the thermodynamic entropy is the max entropy conditioned on the knowledge we use when we operate on the system. Okay, so that's kind of the conclusion of all that. So I hope you have seen with that. I mean, this is, of course, one example of a bigger research area that many people are following. I mean, in Europe, there's even a whole network called the COST network on quantum thermodynamics that just started. So this is one example of a type of statement that one can make that connects information theory and thermodynamics. There are many other interesting examples. I mean, this is such a huge area that I wouldn't want to even try to go through all of them. I hoped that even in that one we couldn't go into details, but I hope you got an impression of how these arguments work. And I think if you learned that if you saw at least that using information theoretic concepts we can make interesting statements about thermodynamics, then you have maybe seen what motivates these people working on these projects. I think we can really learn something new, because such statements wouldn't have been possible without insight. I mean, these are all developments, like this decoupling theorem and so on, are developments that have been done recently. And so these statements rely on all these developments. And therefore, I think I believe this proves somehow that using the knowledge that we now learn in information theory, we can make progress also in other areas of physics, such as thermodynamics, or foundations, as we have seen in the first lecture. So this is kind of the main message of the talk. So I'm happy to take a question, but I would like first to thank you for the attention during the 4 lectures. This will end my series of lectures, and it was really nice. I really enjoyed that the audience was very interactive. There were many questions, so thanks a lot.